Hello, everyone. Welcome to our session on NVMe-oF Fabric. I'm Orit Wasserman. I'm a distinguished engineer in IBM, and I've been involved. Oh. This is Adam. And I actually started with Redis Gateway, switched to OpenShift Data Foundation, and now I'm back in Ceph doing block storage. And with me is Aviv Caro.
I'm Aviv Caro, engineering manager of the NVMe-oF team in IBM. I'm in the storage industry for a lot of years, doing different things, including compression, deduplication, and NVMe-oF. We are going to discuss NVMe over TCP gateway roadmap. I'll cover some topics, and then Orit will continue and cover more topics. So I want to start by discussing some basic NVMe terminology to set the baseline for those who are less familiar with NVMe protocol. And then we'll continue to discuss the gateway. Few basic terms that we need to be familiar with. One is a namespace. So an NVMe namespace is equivalent to iSCSI and FC LUN. The formal definition is a collection of LBAs. And in Ceph NVMe-oF gateway, a namespace is mapped to an RBD image. Then we have the NVMe subsystem, which is really the main entity of the NVMe protocol. So the initiators, the hosts, when they connect to a subsystem using IP address and a port, and then they are connected to the subsystem. The subsystem is really a container of, or contains a lot of namespaces and other NVMe elements, such as NVMe controllers. And the subsystem is identified by an NQN, which is an NVMe qualified name. Then we have the NVMe I/O controller. We have other types of controllers, but let's talk about NVMe I/O controllers. So whenever an initiator, a host, is connecting to an NVMe-oF target, so an NVMe I/O controller is created for that host, specifically on that target IP address and on that subsystem. So if the same host connects to many subsystems, there will be a lot of I/O controllers on the target side, on the NVMe over TCP gateway, on the different subsystems. So we can see an example here in this drawing that we have an initiator that made two connections to the NVMe-oF gateway target. In this example, we can think about two different IPs, and we can see that we have two NVMe controllers. Both controllers serve IOs to the same namespace, and eventually the IOs are landing in the RBD, Ceph RBD image. Okay. Yeah. So let's get back to talk about the gateway, Ceph NVMe-oF gateway. So we support multiple gateways on the same Ceph cluster. And why do we need multiple gateways? So first of all, we want to distribute the load of the NVMe over TCP across as many Ceph nodes and gateways as possible. And of course, we also want to support high availability. So in a case that one of the gateways is down for whatever reason, or the Ceph node is down, or the gateway is down, we automatically direct the I/O to one of the surviving gateways. So there is no single point of failure. So that's why we allow multiple gateway groups, multiple gateways on the Ceph cluster. We'll discuss about gateway groups soon. We also allow to define multiple subsystems on the same NVMe-oF gateway. And this, for example, for the case of multi-tenancy, it's very important because we can define the access control of the initiators per subsystem. So that's one thing that's important in that. We support Linux initiators and ES6 initiators. Okay, so how the gateway is built? So the gateway is actually running in a container, and within the container we have the control plane and the I/O path. The control plane is the management of the gateway. It's taking care about saving the configuration, reading the configuration, updating the configuration, as well as provide a management API through gRPC. And we support MTLS to secure the communication to the management interface. And then we have the I/O path, which is implemented by SPDK. So what happens is that the control plane is configuring the SPDK, and then the SPDK is doing the I/O path. And we also have another piece here that we are not showing in this drawing, but this is related to high availability, so I will discuss it on the next slides. So just a little bit about NVMe-oF discovery. So the purpose of the discovery is for the initiators to be able to discover all of the subsystems and IP addresses that it can connect on a certain NVMe-oF target. Now, because we have multiple gateways on the Ceph cluster, when the host sends discovery command to either one of the gateways in the group, let's think we have one gateway group for a minute. So the discovery command that is getting to any of the gateways in the group will return the list of all subsystems and all IP addresses of all the gateways in that Ceph cluster. And why is this? Because when the host connects, so after the discovery, the next step for the host is to do the NVMe connect. And we want the NVMe connect to be multipath. We don't want a single path. So that's why the discovery is returning all of the IP addresses of all the gateways in the group. And then the host will connect to all of the gateways, and we achieve the multipath that we need. Okay, so what is the current status in upstream? So in Reef and Squid, it's a technical preview. In Tentacle, it's production ready. The code is already merged to Ceph main and to the NVMe-oF gateway repository main. We have coverage in tautology, and still the CLI is a separate container in Tentacle. Okay, so let's talk about the roadmap and planned features for Tentacle. So like I said, we have high availability, and to achieve high availability, we need at least 2 gateways deployed on the Ceph cluster. So the way it works is that all the gateways that are deployed in the same group of failover domain, all the gateways read the same configuration. We are using a Ceph OMAP object to save the configuration. So at the end of the day, all of the gateways expose the same subsystems, the same NVMe subsystems, and the same NVMe namespaces. And once again, this is important because if one of the gateways go down, no problem. The host can continue the I/O on the other gateway, which sees exactly the same picture and is updated. Yeah, so just a word about gateway groups. So a gateway group is a set of gateways that share the same configuration, so expose the same subsystems and the same namespaces, and then the initiator connects to all gateways in the group and achieve multipathing. It can get failover and so on, but we can also define more gateway groups on the same Ceph cluster. So, for example, if you have some reason to do a resource, to divide the resources between different Ceph users, you can say, okay, these users can use this gateway group, other users can use that gateway group. If you want to run more gateways on a Ceph cluster, that's another reason that you might want to use gateway groups. So that's about gateway groups. Okay, so for high availability, the host must be connected to all of the gateways, like we discussed before. You can think of a gateway as a path between the host and the namespaces and the namespace. Okay, so each gateway is another path. Host connects to all the gateway, we get multipath. Per namespace, it's active passive. So when the host connects to the gateway group, it will the I/O path will be optimized on one of the gateway in the group each time, but we load balance the namespaces across the gateways. So like if you have, I don't know, 100 namespaces, by default, 25 namespaces will be optimized on each one of the gateways. And then in the case of a failover, one of the surviving gateway will take over the 25 namespaces of the gateway that died, and the host will route the IOs of these namespaces through that gateway. Okay, so to implement just how did we implement high availability? So we are using the NVMe ANA protocol, which is equivalent to SCSI ALUA. It's asymmetric namespace access. Each gateway is like an ANA group. I know many people maybe are not familiar with this protocol, but in very short, each gateway is responsible for one ANA group. And ANA group is like a container of namespaces. So once again, for the example I showed before, if we have 100 namespaces, we have 4 gateways. We get 4 ANA groups. Each ANA group will have 25 namespaces. And then each ANA group is optimized. So the ANA group has this NVMe protocol specification that it can be optimized or it can be inaccessible. So each gateway on a good path I/O, each gateway will be the owner of one of the ANA groups, and each gateway will get one ANA group as optimized. And then, in the case of a failover, we know to give the responsibility of the ANA group that belong to the failed gateway to one of the surviving gateways. And this is, in very short, how we achieve high availability. And obviously, when we are doing this switch, we are also using block listing and other means to prevent any chance of getting the IOs from 2 different passes at the same time. Okay, last thing about the HA. So how do we identify that gateways disappeared or go down to do the high availability? There is a new Paxos service that we implemented as a part of the Ceph monitor. It's called the NVMe-oF monitor. And so the NVMe-oF monitor is responsible to identify if any of the gateways in the group disappeared. The way it works is that all of the gateways are sending beacons to the monitor. And if the monitor is missing a few times the beacons from one of the gateway, we assume that that gateway is dead. We start the failover process, which is about ANA group IDs and what I described before. And eventually, one of the other gateways is taking over. And obviously, the other, for failback, once the monitor identifies that that gateway came back to life. So we are doing failback. We are returning the ANA group to the original owner of that group. Yeah, Orit, you're next. Thank you.
So now I'm going to go over the different features we add, because AJ was the biggest feature we had to add. Without AJ, it's not ready for production. But now we can actually focus on other areas and improve the gateway. So the first one is making easier to use, lots of usability features. As we use SPDK, we get many things for free. This is one of them, quality of service. SPDK support for quality of service. We add API to configure it, and you can specify for a namespace how many IOPS, maximum IOPS, maximum bandwidth, maximum read, write IOPS. This is per namespace and per gateway. We are not doing distributed QoS, maybe one day, but it's very complex to do distributed QoS. Aviv mentioned load balancing. So when you create a namespace, we basically look at the gateways, find a gateway that is, we use one robin, and we try to distribute the namespace across the gateways. But as we know, things happen. So if you remove a gateway, we do already implement the code in main that handle it and move the namespaces and spread them between the gateways. But if you increase the cluster or delete namespaces, you may get imbalance, and then we need to rebalance. So what we'll have in technical, we'll have the CLI to do it, but you need to do it yourself. We are working on doing it automatically. Hopefully, it will land in technical, and basically we will have a background process in the monitor that will detect that the gateways are not balanced from load, and it will rebalance it. This is an example how you can see it. CLI, so as Avi mentioned, currently the CLI is a separate container, and then you need to run this very long line. You can alias it, so it will be a bit shorter, but it's very cumbersome. You need a container. We want to make the CLI part of Ceph CLI, and basically that you can use the regular Ceph CLI. This is work in progress. Also, we're planning to have it in tentacle. This is the dashboard team is working on that. And dashboard, so the dashboard didn't make it to Squid either. The dashboard is coming to tentacle. It's already merged in main. You can create the services, the different gateways. You can create subsystem, create namespaces, everything using the dashboard. Very nice. I hope you try it and give us feedback if we missed anything in there. More management. We enhancing the dashboard, more workflow, multi-group, and multi-namespace workflow to make it easier. Alerts and monitor, we have already in alerts and monitors. You can see the NVMe-oF gateway status in self-health, but there's always room to improvement. We're adding more alert about misconfiguration, alert about error conditions, that also coming up. This is more about SPDK. So SPDK default mode of working is with huge pages, which are really good for performance, but a bit of friction. You need to allocate them before, and they are pinned. And you don't always need the performance, or maybe you're just doing testing and you just don't have enough memory to do the huge pages needed. So newer SPDK will have a no huge page option. We're going to support it as well. Big caution, if you need the performance, you have to use huge pages. It's a big performance impact not using it. VMware support, so many users want the NVMe over TCP in order to connect the VMware to Ceph. We support the VAI, which is the basic API needed for VMware VMFS, but we want to extend the support. We have VASA API, which is basically storage API to monitor and see the state of the storage as part of your vSphere console. We're going to support that, add an additional API. And then there's Vivo. That's the new way of managing storage in VMware. Those require us adding new API to the gateways, supporting much, much larger scale of namespaces, as every Vivo will be actually 3 RBD images. So this is work in progress, probably after Tentacle. Security. Security is very important. This is a network protocol. You access it remotely, and you should care of security. As Aviv mentioned, by default, the protocol has access control by using a subsystem masking. You can tell this subsystem allows only this list of hosts using the NQN of the host. Everything in NVMe is NQN. And only those hosts can actually connect to that subsystem. So this is in. It's in from the beginning. It's part of the protocol. You can use also the wildcard, and that means everybody can connect to the subsystem. I really highly recommend not doing it. Please specify, use your access control. Another thing, we have already encryption in transit. NVMe-oF, one mode of TLS, it's called PKS, pre-shared keys. It means you actually need to provide the keys before. It's harder to manage, but it's in. We provide CLI to configure it and to use it. Main issue, TLS is hard, and none of the, it's in the Linux upstream, but the downstream version of Linux initiators still are not supporting it, and also not ES6. So currently, the only one I know, you can either use the upstream Linux kernel initiator or the SPTK initiator to actually use it. It does plan to come. I think it's now tech preview in the latest well, and it's going to GA later. I haven't looked about Ubuntu. MTLS, as we've mentioned, we provide APIs, and also the CLI talks with the gateway using gRPC. We wanted to secure it. We provide MTLS, mutant TLS. You configure it as part of the service configuration using Ceph ADM, and then the communication between the client to the API are completely encrypted. All of those in. What are we working on? So subsystem granularity for access control is not enough. The moment you allow a host to connect to a subsystem, that means it can actually see all the namespaces in the subsystem. So one option is to use different subsystems for different hosts, but that can be quite complex because you sometimes do want some sharing. We are providing namespace masking. You can actually give a list of hosts that can access a namespace. It shouldn't be a huge list, not thousands of hosts, but it's going to be optional. In this case, for example, we limited namespace 10 to only 4 hosts can use it. Many cases, it could be even just 1. This is much safer, much better granularity for access control. This will come in Tentacle. Inbound authentication. And important to say, authentication is not access control. Authentication is making sure that the initiator, when he's connect, it's really the initiator and not somebody impersonated, or the other way around. So this uses, whoever knows, iSCSI, CHAP protocol. And you can actually define if you use authentication or not per subsystems. And as you see, it's unrelated to TLS. TLS is encryption of the in-transit traffic, and CHAP is about authentication. So we have 2 types. Yes, unidirection means we only authenticate the initiator, and bidirection means that the initiator will also authenticate the target, the gateway. But again, this is not access control. For access control, you need to use subsystem and namespace masking. This only makes sure that when an initiator connects, it's really the initiator The moment it connects, it can access whatever the access controllers allow. So now for my favorite part, performance at scale. So SPDK, we have quite good performance using SPDK. It's really good. And we get good IOPS. So first of all, let's talk about scale. So we usually limited our scale. Sometimes it's the implementation limiters. In most cases, it's about resources. SPDK uses lots of CPU, and also libabd sometimes. So we don't want to have huge gateways. So we limit how much we support, but many cases, if you probably give more, it will be fine. But we haven't tried it. So currently, we support, in technical, we're going to support 8 gateway groups in 8 gateways in the gateway groups. We're going to increase it to 32 in the future. 4 gateways in the cluster currently. It's going to be supported. 4 gateway groups in the cluster. It's going to go to 8. 128 subsystems in technical, twice as much in the future. Namespace, we currently limited to 1,024 namespace in the group. We're going to support twice as that. And currently, we hosts per subsystem mean connected hosts to a subsystem. Again, this is about resources. The more hosts are connected, you need more controllers. Those take lots of resources. So currently, it's 128. We're going to double it in the future. But let's talk about performance. So this was done on not the latest main version, but actually the one more similar to Squid Plus. It's done on RHEL 9.4, on Ceph 18.2, but with additional of the NVMe-AJ. And this is mapped to the downstream IBM Ceph 7.1. This is done on all Ceph Dell hardware. So first of all, a bit of explaining what we have. So SPDK has this abstraction called BDEV, block device. BDEV is basically mapped to a namespace. And we map it to a namespace to RBD image. When we here talking about number of BDEVs, it's actually not number of namespace, but how many Ceph contexts we allocate per namespace. As more BDEVs, it's more resources, more Ceph contexts, lots of more resources, Ceph contexts. Actually, here at part 5, but yesterday Ilya corrected me that it's actually 11. So 11 threads per Ceph context. It's not only, so it's 2 for libRBD, 3 for messengers that go and other components, and also memory, tens of mega. If we want to support 1,000 namespaces, and we'll do a Ceph context per namespace, we're basically going to we'll have tens of thousands of threads, and we need lots of tens of giga memory. We cannot have it, so we limited. Our default is allocating 1 Ceph context per 32 namespace or 42 BDEVs. So here we actually looked what will happen if we actually our default compared to doing 2 BDEV. This is the parameter called BDEV per cluster, but that means for every 2 namespaces, we'll have a Ceph context. Another thing we can control is the SPDK reactors cores. Our default is 4. It means we allocate 4 cores for each reactor owns the core, and usually 100% CPU because it uses polling. So we'll have here, with 4 reactors, you have at least 4 cores for SPDK, and you need additional cores for libRBD and the Ceph context. So it's actually like 16. Here we actually tried it with 10. So you can, and also we increased the number of OSD, not the number of gateways. Interesting enough, this is latency versus IOPS versus latency. And you want to see an hockey stick, the flat one. So you can see that with more reactors and using BDEV too, you can actually see a very nice hockey stick. With the default, it's less nice. So we actually see the spike in latency. Another thing interesting is that the more SD, it does get better. But at a certain point, without increasing the Ceph context, and it gets worse. So that's interesting. So when you actually run your workload, you can tune the BDEV per cluster, assuming you have enough memory, and play with it to fit your workload. In the future, hopefully, you can do it automatically, but that's more complex. Another thing, we want to make sure we're scalable. So this is basically increasing the cluster, increasing one gateway per node. And as we can see, we scale linearly. We only had 12 nodes, so that's what we tested. And not surprisingly, 16K does better than 4K. Ceph is always better with larger. I assume if we would test 1 mega, it'd probably also be better. And this one is interesting about actually adding OSDs to the cluster, not increasing the number of gateways. And you can actually see the more OSDs, you can see much nicer graph, much more stable from latency perspective, and also get more throughput. Without increasing the number of gateways, this is still 4 gateways. So this is likely, and it's not surprising, I think anyone knows, larger Ceph cluster, not too large, but larger Ceph cluster will bring you better performance and will be much more stable. So this is actually really cool. So what are we doing for performance? So first of all, the number we choose to how many Ceph contexts per BDEV currently is configurable, is static, and our defaults probably should be better. So we're going to change the algorithm for allocation and make it better. Default will be better. Currently, it's 1 per ANA group because of the J and block list, but we don't need it. We're going to make it lower. Then we want to reduce the number of threads. The threads and memory and too much. That's why we cannot do one Ceph context per BDEV. One option is using a thread pool, but after today, Dev Summit, Ilya mentioned that will also affect libradius. It won't be just in librd, and that means we'll need to handle block listing, which makes it a bit more complex than what I thought. So I don't know when to get it, but I hope identical. And the much future direction, we have SPDK. SPDK uses reactor model. Why not do it the same? We have some Crimson, who's also a reactor model. Let's rewrite librd and also libradius that actually can be a reactor, and we can use the SPDK reactor scheduler. And this way, we can reduce copy. It's much easier to scale. It's easier. We don't need, currently, we, for example, allocate separate thread cores for SPDK and separate for librd. In this model, we won't need to do it. So lots of cool stuff, but this requires a big rewrite. Another thing we notice, in many cases, the messenger is using a 100% CPU and becomes sort of the bottleneck, especially if you have modern 100 giga network. We need to improve it. This is out of the gate, but we should look at it. Again, thread pool, too many threads actually cause lots of context switches and locking, which actually don't scale. And we should allocate by default more threads for the messenger, especially if you know you're going to do high-performance workload. We need to reduce the CPU usage because we looked at the messenger and that it does data copies, which we shouldn't do, if possible, ever. And also if you can use zero-copy network, because currently, because we are user space, so we have from kernel to user space and back, we want to avoid it as well. This one is not more about performance, but it's about sustainability and power usage. SPDK by default is polling. He uses 100% of CPU. When you do top, you always see the SPDK reactor, 100%. This is the way SPDK. SPDK is a new scheduler. It's dynamic. It can switch between interrupt mode and polling according to the load. It's very new, so it's not. I think it will take it a version or two to be more stable. It has a penalty, because if your workload is quite static, then it's cool. It's actually going to switch once, and that's it. But if you basically move all the time between the interrupts and the polling, then you actually have serious reduction in performance. But that's future. And I think NVMe-oF is very easy to use hardware accelerators. We discussed in the Dev Summit CRC calculation of offload, for example, in Intel DSA, data stream accelerator, I think, with the coprocessor. Looks really promising. As we do lots of CRC calculation in LibRVD. Encryption, you can offload it to Intel QET and other accelerators, and you can offload TLS to the NIC. Here, I want to comment, currently, this will be good for NVMe-oF when we use TLS. Sadly, for the messenger, we don't use TLS, so we cannot offload. That's something we need to consider if we want to switch to use TLS in the messenger, and then, or something compatible, so we can offload all the TLS stuff to the NIC. So I think you can see we're working really hard on the gateway. We're adding lots of stuff. We'll be happy to get your input. What is missing? What is good? What is not good? We're happy if you join our calls. We have a weekly call every Tuesday at 7 a.m. Pacific. We plan to switch it to bi-weekly because not lots of attendance. I hope you actually come and join. We'll be happy, raise topics. And we're happy to have contribution, bug reports, anything when anyone is using the gateway and want to give us input. And I don't know if I have time to question or not, because we started 5 later, so I think we should have time. I don't know.
40, until 11:40, I think.
So we have time for questions?
Next session starts in 4 minutes.
Yeah.
Oh, 4 minutes. So 4 minutes of questions. Or maybe you need to go, so maybe I'll free. Here, Mike.
So I was curious in the performance numbers, when you added the OSDs to the default, did you see any bottleneck in the NVMe-oF that caused that drop off?
No. Okay, so Mike asking, so when we added OSD, did we see any bottleneck in the NVMe-oF? No. It was usually either not enough Ceph context, which is more basically less connection to the OSDs, or the messenger.
So is that going to be a recommendation as you have a larger cluster?
So Mike said, will we recommend having more Ceph context if you have larger cluster? Again, it depends on your workload. Maybe you're fine. You have few namespaces, and it's fine. Maybe you'll need more Ceph context. We need to actually measure it before we recommend it. Any more questions? Yeah, Matt.
Well, it's definitely working on parallel, running at zero copy for MS through Opticur and Messenger. I think it gets through Opticur. Maybe you guys can talk more about that if there's going to be more work done. It's actually possible in ASIC Messenger to
Cool. So Matt said there's work looking at zero copy for NFS, doing zero copy in the objectors, so we should talk. Any more questions? So thank you.